The purpose of this video is to explain how to use graphical methods to find unknown forces in situations where the forces are balanced. So that's going to be any situation where your object is at rest or where it's moving with a constant velocity. So in this problem, this example, we have a 65 kilogram box at rest on an incline, and the angle is 37 degrees. And we're supposed to use graphical methods to find the unknown forces. So right away I know I could find one of the forces. I guess this is implied that you could use an equation to find the force of gravity. So let's find the force of gravity first. And that comes out to be 637 newtons. Then we want to draw a free body diagram. So whenever you're working with forces, early in the problem, you should draw a free body diagram showing all of the forces on the object. Whenever you're working with forces on a ramp, I would suggest sketching your ramp with your object shown as a dot on the ramp. That way you can keep track of the directions of your different forces. So we have the force of gravity, which is straight down. The normal force is perpendicular to the ramp. And the friction force is going to be directed up the ramp. The reason that I know the force of friction is up the ramp is that without it, the block would slide down the ramp. So friction is resisting that, and friction is the force that's actually keeping it at rest. So these are the three forces, and we're also going to need to know the angles of these forces if we're going to draw a graphical addition of vectors. So we need to choose a coordinate system. If the object was sliding, I would use a slanted coordinate system, but because the object is at rest, and I find it easier on graph paper to use this kind of coordinate system, I'm going to set up my positive x-axis this way and my positive y-axis this way, which means I have two forces that I need to find angles for. If this angle is 37 degrees, what would this angle be for the force of friction? Well, these look like similar triangles here, so this is also going to be 37 degrees. We're also going to need to know this angle for the normal force. Use geometry and figure out what that angle is. To find that angle, I see that in this triangle I have 37 degree angle, I have a 90 degree angle, and this angle must be 53 degrees since the angles in the triangle have to add up to 180. This here is a right angle, so if this part of it is 53, this part must be 37. This is a right angle. So if this part is 37, this part must be 53. Once you have your free body diagram, you're ready to prepare for drawing the vectors on graph paper. And in order to do that, it's important to create a scale and list your forces. So I'm going to move this aside and list my forces up here. So I have the force of gravity is 637 newtons, and that is down. Be sure to include the direction. I have the force of friction, which I don't know the magnitude, but I know that it's at an angle of 37 degrees. And I have the normal force, which also I don't know the magnitude. It's at an angle of 53 degrees in this little triangle. But if we wanted to give the angle from the positive x-axis, it would be 127 degrees. So that's 180 degrees minus 53. Now we need to choose a scale that will be useful for drawing our graphical diagram. I'm going to choose a scale of 1 centimeter equals 50 newtons. So that means that my force of gravity vector will be 12.7 centimeters long. You want to make these vectors as long as you can when you draw them graphically. It will make your results more accurate. Okay, we're ready now to draw our vector addition diagram. So I'm going to start with the force of gravity vector, which is pointed straight downward. I'm going to start it here so I have plenty of room to fit it on the paper. Maybe even a little higher up. So 12.7 centimeters goes down to here. And label your work. Okay, now we need to add the other two vectors. The really important idea here is that this object is at rest. We have a block on a ramp, it's at rest, which tells us that the forces are balanced. If the forces are balanced, that means that all of the vectors, when we add them together, have to create a closed diagram, because balanced forces means that the net force is 0. So when we add the force of gravity vector, the force of friction vector, and the normal force vector, it needs to be a closed diagram. So we have our force of gravity vector. The next one, you can add these in any order. I'm going to add the force of friction next, and I know it's at an angle of 37 degrees. So when you add vectors, you add them tip to tail. So this is the tip, and then now you need the tail of the next one. So you start your next vector at the place where you just left off. So from this point, I need to find out where 37 degrees is. 10, 20, 37 is right here. So I know the direction of the force of friction, but I do not know its magnitude. So I have no idea how long this force vector should be. So I'm just going to draw it longer than needed, and later I'll be able to figure out where it should stop. So I'm not putting an arrow on yet because I don't know where the force vector ends. Now, this is the trickiest part of doing this. It's adding the third vector. The third vector needs to close the diagram, and the normal force is going to be that vector that is added onto this one, and it's going to end right here. But it needs to be at the right angle. Not meaning 90 degrees, but at the correct angle. In order to do that, we actually have to draw the angle from here, because we do know the angle that it makes with the vertical. So here's how I would recommend doing that. We need to find the angle that the tip of this arrow makes with the vertical. So from this diagram, you need to figure out what that angle is. This angle right here is the one we need to know. So this angle in red. If we know that, then we can work backwards and draw it on our diagram. So if the angle down here is 53 degrees, this is a right triangle, which means that this little angle up here is 37 degrees. Okay, so the normal force, the tip of it, makes an angle of 37 with the vertical. So that means here, this is where the tip of that normal force vector is going to end up. I need an angle of 37 degrees here. So let's draw that vector. So going from the vertical, 10, 20, 30, 7 degrees. So this right here is going to be at 37 degrees. So I'm lining up the finishing point because I need a closed diagram with my mark that shows me 37 degrees. And now I can see how long these vectors are. I can see that the force of friction vector goes to here, and then the normal force vector goes from there to there. So this is the force of friction vector, this is the normal force vector. Okay, recall that the angle here was 37 degrees. these should be perpendicular, so that's another way that you can check your result. If you look back at your free body diagram, remember that the normal force is perpendicular to the force of friction. The very last step then is to convert back to newtons. So we need to measure the lengths of these. This looks like it's about 7.7 centimeters. And I can convert that now back to newtons. And my normal force vector is about 10.2. So 7.7 times 50 is 385 newtons. And 10.2 times 50 is 510 newtons. Okay, and I already have my angles figured out. So the answer to this problem would be that the force of friction is 385 newtons at 37 degrees, and the normal force is 510 newtons at 127 degrees. Be sure that your diagram has arrows on every force vector. Okay, and then just to reiterate, this was a balanced forces problem, so when we added all of the force vectors, okay, all three forces that were on that object, we ended up with a closed figure. The resultant was 0. We didn't have to draw any extra net force vector because these vectors made a closed diagram because that net force is 0.